All right, so good afternoon. My name is David from Spring Technologies. I'll be the facilitator for today's webinar. All right, and just a simple house rule. Please mute your mic if you are not speaking, but please do ask any question along the way. Don't feel shy. All right, just that after you ask your question, please mute it back. All right, and yeah, let me introduce our speaker for today, Dr. Zhang Ming. Dr. Zhang is the founder and principal EMC consultant for Match One Design Limited based in UK. Kindly please mute your mic, gentlemen. All right. Dr. Zhang has in-depth knowledge in power electronics, digital electronics, electric machines, product design. All right, and Dr. Zhang will also have a YouTube channel, all right, where he also talk a lot about EMC. He's one of the very experienced experts in this field. All right, so the presentation will be about 50 minutes. We will have about 10 minutes Q&A, but you don't need to wait until the Q&A to ask a question. At any point of time you have a question, please unmute and ask Dr. Zhang. All right, at the end of the presentation, we will send you this presentation recording and some of the hands-on practical video that Dr. Zhang have recorded for us. All right, so over to you, Dr. Zhang.
Right. Thank you very much, David. Thanks for the introduction. Hello, everyone, and welcome to today's EMC seminar session. In today's session, we're going to talk about troubleshooting techniques for radiated emission and radiated immunity. First, a short introduction of us. As David put it already, we are a small consulting business specialized in the field of EMC, ESD, and signal and power integrity. We have many years of experience, especially with electronics, machine design, digital electronics, and analog electronics. Currently, we cover a wide range of applications. As you can see here, I would say 20 or 30% is industrial application, then 20 to 30% on home appliance, and then the majority of the business share is focused on the automotive section. And as we all know, as the automotive industry is going to the electric vehicle industry, we predict this section of the business is growing, right? So that's where we put our focus is. In today's presentation, so here shows you the outlines of the presentation. We're going to talk mainly two aspects. First part of the presentation will focus on radiated emission, while the second part will talk about radiated immunity. In both sessions, we're going to provide a case study. So the first case study is an automotive head-up display unit used for automotive application. And the second case study is an audio product where you will see, or actually you will hear, the sound quality change when the radiated immunity test was applied on products. Okay. Without further ado, let's move to our first part of discussion, radiated emissions. So you have a product and you want to pass the EMC standards so as you can sell the products. Of course, that means you have to do lots of EMC tests, which include conducted emission, radiated emission, and lots of other tests. In this session, we'll only talk about radiated emission. So traditionally, for testing a product against radiated emissions, you will need to send your product to accredited test house, and then they will charge you lots of money. You have to book a long lead time. These days, every house gets really, really busy. So, and then you send your product, hoping the product will pass the EMC test. And that's it, really. They can only tell you whether your product will pass or fail the radiated emission tests. Of course, the drawbacks we already discussed, including high cost, long lead time, and they can't tell you, they can only tell you whether your product pass or fail. They can't tell you if your product fails, how can you fix the issues. Thus, we really need what we call the pre-compliance radiated emission test. So a pre-compliance radiated emission test is a test that you can perform in your own benchtop setup, in your office, in your factory, and the cost is often very low because you only need a couple of low-cost test equipment. Plus, if you have a spectrum analyzer or an oscilloscope, and then you can quickly perform a pre-compliance radiated emission test. Of course, the disadvantage of pre-compliance radiated emission tests is, first of all, you are facing very noisy ambient noise, as you know, some of you probably have already experienced when you are trying to measure an emission source, let's say. Then you notice that actually the LED lights in your office building play an important role. You know, creates lots of noise floor. So you switch off the lights, and then you realize, you know, the local radio station gives you lots of peaks, maybe in the frequency range between 90 megahertz and 110 megahertz, often the FM band. And then it just happens that your product also produces noise in the same frequency range, so you can't really distinguish them. So that's one drawback. And another thing is, people are quite familiar with the so-called near-field troubleshooting, where you're using a near-field probe. And then, yes, you do see noise. You do see noise in a different frequency range. But how can you translate that near-field measurement to far-field results? Which means, you know, you see the emissions, but is this pass or fail? You can't tell, right? So that's the drawbacks associated with the pre-compliance test. All right, so these are the pre-compliance EMC troubleshooting tools we often use. As you can see, if you can invest a little bit more, I would definitely invest things like antenna, small size antenna, or an open tensile, which is quite useful. But if you don't have a big budget, sometimes a set of near-field probes such as this, or an RF current probe is perhaps all you need. Of course, then you will always need something like a high frequency bandwidth oscilloscope. Often we're talking about at least 500 megahertz, or a spectrum analyzer. I think these days you probably need to choose something up to 2.1 gigahertz at least, okay? One thing I need to point out is the physical limitation of using small size antennas. So, for example, if your product has some emissions between 30 megahertz and 300 megahertz, which is often, you know, the frequency range of interest, and a full-size biconical antenna is often needed. But of course, these days we have smaller size antennas, such as this one. The drawback of the smaller size antenna is because, you know, the size is small. So when you're approaching low frequency range, when we say low frequency range, in this case, it's between 30 megahertz perhaps to 100 megahertz, you ended up with a very high antenna factors here, right, showing here. And what does this high antenna factor mean? This means that when you are using a smaller size antenna and you connect it to your spectrum analyzer, you will find that the noise floor, even you test it in a very, very quiet environment, you will find that the noise figure of the spectrum analyzer is rather high. Sometimes it is even higher than the limit line you are testing against. This is really nothing to do with the manufacture of the antenna. This is really the physics, the limitation of the physics, since, you know, the wavelength and frequency has this fixed relationship. So that's the drawback of using smaller antennas. That's why for near-field probing, near-field troubleshooting, we always prefer magnetic field loops. So this first session, we're focusing on how to use magnetic field loops to help you troubleshoot radiated emissions. The theory of magnetic field loops is very, very simple, right? You have two wires put in parallel, And then we know from Michael Faraday's electromagnetic coupling theory, we know that if you have a very high di over dt, which means the change of current going through wire 1, then if you connect a voltage meter to wire 2, you're supposed to see the induced voltage caused by the mutual coupling between the two wires. So that's really the fundamental theory of magnetic field loops. And how to build a magnetic field loop, right? If of course, we always recommend you to buy the commercial ones, because the commercial magnetic field loops, they often have two features that are desirable. One is they have the shielding capability. That means they measure the magnetic field, but they can also shield the electric field. So that's the first advantage of having commercial made probes. And second advantage is that sometimes they will give you a nice calibrated data sheet, so you can read the data sheet, then translate the measurement results into something meaningful. But if you don't have a commercial set of probes, it's not the end of the world. You can easily build one such as this one showing here. As you can see, as we talked, it works as two conductors in parallel. So in this case, imagine this conductor, this long size conductor is carrying current. Then this side of the loop, this smaller size conductor, I would say 2 centimeters long, will have some induced voltage when you have a high di over dt going through this first conductor. These two sides, these perpendicular sides of the loop, will not induce any voltage, simply because they are perpendicular to the current carrying conductor. And this side of the loop, since it is quite far away from the main current carrying conductor, it will also not induce much voltage. So really what you are measuring is the voltage induced on this 2 centimeter long conductor on the loop. Okay. So here's a simulation, basically simulates a very simple magnetic field loop. We can, we try to simplify things. We can simplify a magnetic field loop having some self-inductance and some mutual inductance, as we show here, right? And then if you plot the voltage response and current response curve, you will see that it has a very flat response up to about 100 megahertz, which means, for most of the signals we're dealing with daily, we can really measure the signals, and we know that the result of the signal is a di over dt, right? It's di over dt. So having that in your mind, you know that when we are using a magnetic field loop, we're measuring di over dt. Okay, so what does that mean translating to real life? Here we're using a Texas Instrument DC-DC converter. This is a buck converter for demonstration. There are two ways of using a magnetic field loop. You can place the magnetic field loop horizontally, right, towards your PCB, such as the one showing on the left. This is often what we call an EMC sniffing exercise. And the way we do it is we make sure that maximum coupling, between the small magnetic field loop and your PCB can be achieved. So what you do is really you just move along the probe over the top of the PCB, and then on the other side of the loop, you're connecting the loop to a spectrum analyzer or an oscilloscope with 50 ohm impedance, right? That's important. The loop needs to be connected to the 50 ohm impedance of the oscilloscope. So with most of the oscilloscopes in the market today, you can select the impedance. You can have 1 mega ohm impedance input or 50 ohm impedance input. But if you don't have that one function, all you can do is you just insert a 50 ohm feed through BNC connectors. That will also do the job. So this is a EMC sniffing exercise. The purpose of this is to identify the hot area. We call the hot area on the PCB. Once the hot area is identified, you see lots of noise in this particular region. Of course, you want to bottle it down to to which trace has the problem or which device has the problem. In that case, you then flip the a small magnetic field loop so as the loop has a perpendicular position to the PCB, as shown on the right. As you can see, we talked about the theory, right? We're using this very short of conductor, right, to form a transformer with any trace or component on the PCB to identify if there's any very high di over dt behavior on the board. And often if you see something on a trace, then that trace needs to be paid attention to. Okay, so this is the test setup. We have again the Texas Instruments PCB connected to 2 listens. This is a very typical automotive setup. It's powered by 12 volts, and this is the PCB we're using. Very, very short or simple explanation of what we mean by we say hot loop, right? Giving a DC-DC converter, for instance. Of course, this is a buck converter, so the hot loop is defined as a loop between the input capacitance and the 2 switches, right? So this is the hot loop area, and this is where the magnetic field predominantly exists. So the bigger the loop, the worse the emission is. And of course, when we talk about converter, we need to talk about the switch node, because this node here, which is the midpoint of a pair of MOSFETs, is a noisy node because it's switching often at 30 to could be 1 megahertz switching frequency, and the switching speed of this pair can be very, very fast. We're talking about maybe 5 volts per nanoseconds or even higher. So these are all the noise source creates the problem. Of course, this is a buck converter example. If we talk about a boost converter, for instance, then the hot loop will move to the output stage, right? And if you're talking about an isolated converter, such as a flyback, then the hot loop, actually, there are 2 hot loops for flyback converter, one on the primary side, one on the secondary side. So these are the areas that you need to pay attention to when you are designing a switch mode power supply. Again, we do some very simple simulation just to give you an idea. This is the buck converter simulation we did, matching results with the Texas Instrument PCB. As you can see here, what we're trying to demonstrate here is that this is the position of a magnetic field loop. This is another position of the magnetic field loop. As you can see, that really the output voltage of the magnetic field loop is a di over dt result. So for example, if I measure the voltage drop across this inductor, then I get something like a square wave voltage shape, which is the same as my voltage here. However, if I press the magnetic field loop against a trace on the alongside the hot loop, what I expect to see will be something like this, like a very spiky waveform here. And this is actually what we saw if we do this. As I said, if I move the magnetic field loop close to this inductor, then I measure a square wave voltage waveform. And then the scope, if I use the scope and then do a integration calculation, then I can get the current waveform. So that's how I arrive at the current waveform. And of course, if I move the magnetic field loop close to a trace area or just a PCB ground area, then I pick up all these spiky waveforms, right? As the same as we just saw in the simulation results. So this is a further demonstration. Basically, you can just move along the magnetic field loop on the PCB and then try to see areas where you can see a big di over dt in the system. And as we explained, the big di dt often is the source of your radiated emission. So the question really is, for example, in this case, I measured using the small magnetic field loop, and I measured the peak-to-peak voltage. In this case, as you can see here, is about I think it's I can't see 20 millivolts. Okay, so this is about 100 millivolts peak to peak. The question is, would this cause radiated emission problems? Right? As we said it before, the problem with near field probing is that you see the noise, but how to translate into far field performance? Well, in this case, it's all about experience and your application. For example, if this board is to be used as a home appliance product, I probably wouldn't worry about it looking at this 100 millivolts peak to peak. But if the board is going to be used for an automotive application, because of the very stringent limits that automotive test standards is, so I will probably do something about it. Okay. So here gives you an example. This is a case study. It's a product used in a head-up display. You can see here we have the simple conducted emission test setup. We test the product on a ground plane with listens and spectral analyzers. Everything's powered up. And as you can see here, we just did a very quick scanning between 150 kilohertz to 30 megahertz, right? The standards actually test against up to 100 something megahertz, but we knew the problem really is in the lower frequency range. So we just did a scanning there. As you can see, all the peak of the emission are marked up and they're quite high, you can see here. So the next step is took the PCB out from the product and only tested the PCB performance, right? So the same setup is that the difference is I'm only testing the PCB. By testing the PCB, and also I narrow down the frequency range to 16 megahertz, what I noticed is that there are some, dominating frequency spectrum here, but there are also a neighboring frequency noise, which sits quite close, right? Here you can see these two are close, but what is close is 4 and 5. You can see 4 and 5, they're close, right? Quite close. Considering the resolution bandwidth is 9 kilohertz, so these two are fairly close. If you reduce the resolution bandwidth, let's say to 1 kilohertz, you will see more clearly these two are actually two spikes rather than one spikes. Same apply with 6 and 7. So there are two dominate frequency there. Okay, so that's everything scanned using a listen setup. We know the frequency range that could cause problems. So the next stage is to find which part of the circuit caused a particular issue. So we're introducing the magnetic field loop to locate the noise source. The technique is the same as we just discussed. Move a small loop alongside the PCB and I identify the spikes and I measure the frequency between the neighboring spikes. Then I identify a 2.1 megahertz, right? So this 2.1 megahertz noise comes from a switch mode power supply circuit, which is here, as you can see here. You can see this is the the inductor they use. This is a Worth shielded inductor part. This is the IC. So this small, very, very small switch mode power supply cause 2.1 megahertz noise issues. And it's interesting because, as you can see, even if I move this loop quite far away from where the switch mode power supply is, I still pick up very high DI over DT noise. So that's not good, right? That's not good. That means the noise propagates into the whole system. So that's something you need to really pay attention to. Okay, then using the same technique, we are able to locate the second noise source, which is a 1.8 megahertz noise source. As you can see, 1.8 and 2.1, quite close. That's why we see the neighboring spikes. Same as the 2.1 megahertz noise. This one also, the noise propagates. As you can see here, I place sort of close to this inductor, I pick up noise such as this, right? Quite high level. But look, I moved almost to the other side of the PCB. This is like at least 1 centimeter away. I can still see noise, right? So the noise is not well controlled, let's say. So how to fix the problems, right? So we identified 1.8 megahertz and 2.1 megahertz switching noise. Now the next step is to fix them. But to fix them, we have to know how the noise is coupled to the system so as they can propagate to the whole PCB. Well, in the case of the 1.8 megahertz noise, what we saw is, right? So I highlighted here, this is an input stage filter, okay? In this yellow shades here. This is the blue, this blue shades outline the output stage filter. And if you notice, these two are placed on the layout in parallel. And this is a very bad design because you place the two filter stage in parallel. Effectively, you are giving a very good parasitic capacitance path between the two, which means lots of the filters you implement will not be effective. So you spend money and time developing these filters, only these filters are not doing a good job. So that's the main reason of this noise. So how can we prove this, right? So the way I prove it, first I actually moved one of the inductor on the input stage further away. As you can see here, there are two twisted lines here. That is where I moved the inductor from this point further away, but that doesn't help because these two cables also couple noise. So the next stage, what I did is simply shoot the whole output stage filter, right? Using a copper tape. But the copper tape needs to be bonded and have a very good electric connection to the grounding point, which is here, okay? So I place this and then we test the conducted emission again. As you can see here, the purple one is the bare PCB, the result we got previously, right? And then when we apply the shield, just look at the result. We achieve at least 5 to 10 dB reduction. 5 to 10 dB reduction, that's a lot. Simply by just covering the output stage filter. So this does give a good indication. That means the input stage filter and output stage filter have a very strong coupling, and it affects the EMC performance of this switch mode power supply. Okay, so we found out the reason, but we can't really, because this is a professional, automotive PCB board design, from big companies. You can't just say, oh, put a copper tape, right? So you have to give them really good EMC advice. So in this case, we advise them to basically relay out the switch mode power supply filters. This is the original filter layout. Here shows you the recommended layout. As you can see, first we move the two parallel stage filter into a 90-degree position, right? So this is to minimize the coupling we just discussed between the input and output stage filters. Then details down to input stage filters. We also provide what we call a field cancellation scheme, right? So the field cancellation scheme is that you place the capacitors head to head, let's say. If I give it a close view, so this is your power trace, let's say, and then your ground plane is underneath it. What you do is you put two capacitors in this head-to-head position. That means when the current flows to the capacitor, will create two currents, right, with 180-degree phase shift. So that means the magnetic field between these two capacitors will be canceled out. So that's a very effective canceling scheme we often use. So we provide this, and also we provide electrolytic capacitors here, right? If you look at the previous slides I show here, they have two electrolytic capacitors on the out stage filter, but without any electrolytic capacitors on the input stage filter, which is a big mistake because really you probably don't need those electrolytic capacitors on output, but you do need electrolytic capacitors on the input. Why do you need electrolytic capacitors on input? Well, two reasons. First is electrolytic capacitors store much more energy, right? For higher power switch mode power supplies, you can't just rely on ceramic capacitors to provide that energy. Simply, you cannot. And the second is electrolytic capacitors. They have internal ESR, right? And this EXR is higher than the ceramic capacitors. So people think it's a bad thing, but actually in this case, they damp the systems, right? You look at the input state, you have L and C and L and C, that creates lots of resonance circuits. But having an electrolytic capacitor with larger ESR will help damp the system well. And the third benefit is because the electrolytic capacitors, they all have aluminum can, like a metal can structure. So they block some of the near field fields, right? So these are the benefits of this new filter layout design, right? Okay, so here, is another example. I think this is I got from some data sheets. They use the same trick, having two capacitors head-to-head provides the field cancellation. Okay, then that's on the 1.8 megahertz noise side. Now move to 2.1 megahertz noise source, because we just deal with this, and now we need to deal with this. This one also has a few problems. The first is I noticed that their inductor was placed in the wrong orientation, right? Often with these shielded inductor, you can see a dot. Sometimes it's a line indicating that's where the winding starts, right? You need to place that dot on the switch node because that's where the winding starts. And then, you wind the inductor. So the outer layer of the inductor shielded this inner winding. So this provides some kind of electric field shielding capability. If you place it in the wrong way, then experience often tells us you're expecting probably 3 dB to 6 dB more radiated emission noise, right? So that's the first thing we spotted. The second thing we spotted is they have a very large copper pad underneath this switch node, underneath this inductor. This is why, when we move the magnetic field loop, even here, far away from this switch mode power supply, we still see the noise. It's because this is a large switch pad, and this pad, of course, is designed taking thermal consideration, right? But it is an EMC nightmare. It's a large size copper, so it radiates more. Okay, so as I said, this is the general filter layout rules. We can give advice to you, right? 3 rules. One is for the well, again, we're using a buck converter here. For the buck converter, the inductor, you better use shielded inductor and make sure that the dot or the line placed on the switch node here. And then you need to have a very clear physical separation between the input capacitors and filter stages, right? For filter stages, you don't necessarily need shielded inductor, right? So that can give you some saving, cost saving. But you need to make sure that the near field coupling we just discussed is not there. Okay. All right. So that's the first discussion. We focus on radiated emissions. Now